We'll be talking about managing growing projects with packages, crates, and modules. As you write large program, organizing your code will become increasingly difficult. By grouping related functionality and separating code with distinct feature, you will clarify where to find code that implements a particular feature and where to go to change how a feature works. The program we have written so far have been in one module in one file. As a project grows, you should organize code by splitting it into multiple modules and then multiple files. A package can contain multiple binary crates and optionally one library crate. As a package grows, you can extract parts into separate crates that become external dependency. This chapter covers all this technique for very large project comprising a set of interrelated packages that evolve together. Cargo provide a workspace, which we will cover in the cargo workspace section in chapter 14. We will also discuss encapsulating implementation details, which lets you reuse code at a higher level. Once you have implemented an operation, other code can call your code via its public interface without having to know how the implementation works. The way you write code defines which parts are public for other code to use and which parts are private implementation details that you reserve the right to change. This is another way to limit the amount of details you have to keep in your head. A related concept is scope. The nested context in which code is written has a set of names that are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct in a module, constant, or other item, and what that item means. You can create scope and change which names are in or out of scope. You can't have two items with the same name in the same scope. Tools are available to resolve name concepts. Rest has a number of features that allow you to manage your code's organization, including which details are exposed, which details are private, and what names are in each scope in your program. These features, sometimes collectively referred to as module system, include package JS, a cargo feature that lets you build, test, and share crates. Creates a tree of modules that produce a library or executable. Modules and use let you control the organization, scope, and privacy of paths. Paths, a way of naming an item such as struct, function, or module. In this chapter, we will cover all these features, discussing how they interact, discuss how they interact, and explain how to use them to manage scope. By the end, you have a solid understanding of the module system and be able to work with scopes like a pro. The first part of the module system we will cover are packages and crates. A crate is the smallest amount of code that the Rust compiler considers at a time. Even if you run Rust C rather than cargo and pass a single source code file, as we did all the way back into writing and running a Rust program section of chapter 1, the compiler considers that file to be a crate. Crate can contain module, and the modules may be defined in other files that get compiled with the crate, as we will see in the coming section. A crate can come in one of two forms: a binary crate or a library crate. Binary crate are programs that you can compile to an executable that can run, such as a command line program or a server. Each function must have a function called main that defines what happens when the executable runs. All the crates we have created so far have been binary crates. Library crates doesn't have a main function and they don't compile to an executable. Instead, they define functionality intended to be shared with multiple projects. For example, the rand crate we used in chapter 2 provides functionality that generate random number. Most of the time when Rustation says crate, they mean library crate, and they use crate interchangeably with the general programming concept of a library. The crate root is a source file that the Rust compiler starts from and makes up the root module of your crate. We will explain modules in depth in the defining modules to control scope and privacy section. A package is a bundle of one or more crates that provides a set of functionality. A package contains a cargo.toml file that describes how to build this crate. Cargo is actually a package that contains the binary crate for the command line tool you have been using to build your code. The cargo package also contains a library crate that the binary crate depends on. Other projects can depend on the cargo library crate to use the same logic the cargo command line tool uses. A package can contain as many binary crates as you like, but at most only one library crate. A package must contain at least one crate, whether that's library or binary crate. Let's walk through what happens when we create a package. First, we enter the command cargo new. After we run cargo new, we use ls to see what cargo creates in the project directory. There is a cargo.toml file giving us a package. There is also an src directory that contains main.rs. Open cargo.toml in your text editor and note there is no mention of src/main.rs. Cargo follows a convention that src./main.rs is the crate root of a binary crate with the same name as the package. Likewise, cargo knows that if the package directory contains src/lib.rs, the package contains a library crate with the same name as the package, and src/lib.rs is its crate root. Cargo passes the crate root files to RSC to build the library or binary. Here we have a package that contains src/main.rs, meaning it only contains a binary crate name my dash project. If a package contains src/main.rs and src/lib.rs, it has two crates, a binary and a library, both with the same name as the package. A package can have multiple binary crates by placing files in the src/bin directory, and each file will have a separate binary crate. Defining module to control scope and privacy. In this section, we will talk about modules and other parts of the module system, namely paths that allow you to name items, the use keyword that brings a path into scope, and the pub keyword to make items public. We will also discuss the as keyword, external packages, and the glob operator. First, we are going to start with a list of rules for easy reference when you're organizing your code in the future. Then we'll explain each of the rules in details. Modules cheat sheet. Here we provide a quick reference on how modules path, the use keyword, and the pub keyword works in the compiler, and how most developer organize their code. We will be going through examples of each of these rules throughout this chapter, but this is a great place to refer to as a reminder of how module work. Start from the crate root. When compiling a crate, the compiler first looks in the crate root file, usually a src/lib.rs for a library crate or src/main.rs for a binary crate for code to compile. Declaring modules. In the crate root file, you can declare new modules. Say you declare a garden module with mod garden. The compiler would look for the modules code in these places, in line within curly bracket that replace the semicolon following mod garden in the file src/garden.rs. In the file src/garden/mod.rs, declaring submodules. In any file other than the crate root, you declare submodules. For example, you might declare mod vegetables. In src/garden.rs, the compiler will look for the submodules code within the directory name for the parent module in these places, inline directly following mod vegetables within curly brackets instead of the semicolon. In the file src/garden/vegetable.rs, in the file src/garden/vegetable/mod.rs. Parts to code in modules. Once a module is part of your crate, you can refer to code in that module from anywhere else in that same crate, as long as the privacy rules allow using the part to the code. For example, an asparagus type in the garden vegetable module would be found at crate garden vegetable asparagus. Private versus public. Code within a module is private from its parent module by default. To make a module public, declare it with pub mod instead of mod. To make items within a public module, public as well. Use pub before the declaration. The use keyword within a scope. The use keyword creates shortcuts to items to reduce repetition of long path in any scope that can refer to garden. And so create garden vegetables asparagus. You can create shortcut with use create garden vegetable asparagus, and from then on you will only need to write asparagus to make use of that type in the scope. Here we create a binary crate name backyard that illustrates these rules. The crates directory, also named backyard, contains these files and directories. So it contains cargo log, cargo toml, src, garden vegetable.rs, garden.rs, and main.rs. Okay. Then in the create root file in this case is src, and it contains, okay, so src main contains this. Okay, src main contain this. The pub mod garden line tells the compiler to include the code in its first src slash garden.rs, src garden.rs. Okay, garden.rs. Mod garden. Here pub mod vegetable mean that src garden vegetable.rs, src garden vegetable.rs. Grouping related code in modules. Grouping related code in modules module let us organize code with in a crate for readability and easy to use. Modules allow us to control the privacy of item because code within a module is private by default. Private items are internal implementation details not available for outside use. We can choose to make modules and the item within them public, which exposes them to allow external code to use and depend on them. As an example, let's write a binary library crate that provides the functionality of a restaurant. We will define the signature of function but leave their bodies empty to concentrate on the organization of the code rather than the implementation of a restaurant. In the restaurant industry, some parts of a restaurant are referred to as front of house and others as back of house. Front of house is where customers are. This encompasses where the host sit, customers servers take order and payment, and bartenders make drink. Back of house is where chef and cook work in the kitchen. Dishwashers clean up and managers do administrative work. To structure our crate in this way, we can organize its function into nested modules. Create a new library named restaurant by running cargo new restaurant dash dash lib, then enter the code in listing. Okay, so he has created a mod and which has two more mods, hosting and serving. We define a module with the mod keyword followed by the name of the module. In this case, front of house. The body of the module then goes inside curly brackets. Inside modules, we can place other items, as in this case with the modules hosting and serving. Modules can also hold definition for other items such as struct, enum, constant, and traits. By using modules, we can group related definitions together and name what they are related. Programmers using this code can navigate the code based on programs based on the group rather than having to read through all the definition, making it easier to find the definitions relevant to them. Programmers adding new functionality to this code, we would know where to place the code to keep the program organized. Earlier we mentioned that src main rs and src librs are create roots. The reason for their name is that the contents of either of these two files from module name create at the root of the creates module structure known as a module tree. This tree shows how some of the modules nest inside another. For example, hosting nests inside front of house. The tree also shows that some modules are siblings to each other, meaning they are defining the same module. Hosting and serving are siblings defined within the front of house. If module A is contained inside module B, we say that module A is the child of module B and module B is the parent of module A. Notice that the entire module tree is rooted under the implicit module name root crate. The module tree might remind you of the file system's directory tree on your computer. This is a very apt comparison. Just like the directories in a file system, you use modules to organize your code, and just like files in a directory, we need a way to find our modules. So see you in next video.